Hi folks. I want to talk about Cartesian coordinates and polar coordinates, perhaps talk about a few things we didn't get a chance to discuss in class. So to review, Cartesian coordinates are the classic sort of coordinates you've been using most of your mathematical lives. So points in the plane sort of have addresses. That's an awfully big point. Let's try that again. How about one of these guys? Points in the plane, such as that point, or this point, or this point, have addresses. And the way you get those addresses is you march off a certain number of units in the horizontal and vertical direction. So in this case, this first point here, you go 1, 2, 3, 4, 5, 6, 7 units out. So the first coordinate is 7, and then 1, 2, 3, 4 units up. So the second coordinate is 4. So those are the Cartesian coordinates of that point. Now the other points I labeled, this will have coordinates 4, -5, and this point will have coordinates -3, 2. Now if you take the difference between corresponding x or y coordinates, well, what you're doing is almost finding the sides of a triangle. I say almost because you might get something negative. Let's figure out the distance between a couple of these points, and we'll see the distance formula in action. So I'm going to draw a segment that goes right here from this point to this point, and I can turn it into a right triangle like so. Now I'm going to find this distance between these 2 points. So what I'll do is I'll just take the difference in x coordinates, so that's -3 minus 4, and that's -7. And I'll take the difference in y coordinates, that's 2 minus -5, and that equals +7. Now these aren't the sides of the triangle because I've got this -7, which doesn't make any sense as a side, but that's okay because what we're really doing is 7, -7, if we square it, it's going to be positive anyway. So the Pythagorean formula tells us that that distance d is going to be related to 7 squared plus -7 squared, or 49 plus 49 are 98. And so that tells us that d is the square root of 98. So there's some coordinate geometry in action. We can imagine a different way of assigning an address to each point. So imagine that the plane represents a city laid out in some sort of grid, and previously your addresses would indicate how many blocks over and how many blocks up you were from some reference point, in this case the origin. You could instead decide to describe where you are in the following way. Let's suppose that right at the origin there's some nice reference monument, some sort of spire or something. You could say that if you were here, you could describe your location the following way. You could say, well, I happen to be r units away from the center of town. So that distance is r. Now at this point, you certainly wouldn't know exactly where you are, but you would know that you're somewhere along a circle of radius r. But you wouldn't have pinned down the exact location, so you need one more bit of information. And what that information, a sufficient piece of information, would be how far around you should swing from some reference direction. And we take that reference direction to be the positive x-axis, and we always measure counterclockwise. So the 2 bits of data r and theta serve as an address for the point. And so we would say that the polar coordinates are r comma theta. Now there are some quirky things about polar coordinates. So suppose r theta is the address of this point here. It's not the only address that serves to describe that location, because you could imagine, instead of going around just to here, you could go around all the way and then theta. So this angle would be whatever theta was before, and we will have added 2 pi to that. That means that this same point could be represented by r comma theta plus 2 pi. This also would serve as an address for that point. It gets even more interesting, however. We could go all the way around here to a direction that's just opposite of the direction previously. That angle would be theta plus pi. And if we went r units in that direction, well, we wouldn't be in the right place. So what we can do is go negative r units in that direction, which is to say march backwards, and we get here. So in fact, another set of coordinates, which is perfectly legitimate, would be negative r theta plus pi. And so that would also be a correct set of coordinates in polar form for that point. So here are 3 different collection of coordinates for the same point, and I'll let you imagine how there are an infinite number of other possibilities. So I want to explore the relationship between polar coordinates and Cartesian coordinates quickly. Here's a point. The x-coordinate tells you how far along the horizon you move. The y-coordinate tells you how far along the vertical direction you move. R, we decided, was the distance from the origin to this point, and theta is that angle that we swing around. Now, the Pythagorean formula right off the bat, we see a right triangle, so we know that r squared is equal to x squared plus y squared. And also, if we remember our right triangle trigonometry, we know that y over x is equal to tan theta. So there's a pair of equations relating x and y to r and theta. If we think about right triangle trigonometry a little bit more, you realize that the quotient y over r, i.e. opposite over hypotenuse, should give us sine theta. So we could write y is equal to r sine theta, and similarly x equals r cosine theta. And there's another pair of equations that relate x and y and r and theta. You'll notice this second set is very well suited to give you y and x if you know r and theta. So that pair is really good for converting from polar to Cartesian. You'll also notice that you might have to work a little harder here to use these equations to convert from Cartesian to polar. R is a snap, because it's just the square root of x squared plus y squared. Theta is going to be a little bit ambiguous, because if you remember the behavior of the arctangent function, you have to work a little bit to really find out what the angle is, because the domain of arctan, or I should say the range of arctan, only runs from negative pi over 2 to pi over 2. So you'll have to be aware of this fact as you use this set of equations to find theta given x and y.